Hello everyone, this is Vishal and today I'm going to speak about our assignment 3, which is SPI device programming and pulse measurement. So basically there are two devices here. One is the MAX7219 driver and the second is the ultrasonic distance measurement sensor. So by using these two devices, we try to create a kind of animation based on the distance measured. So let us look into this. First of all, uh, we use a Max 7219 driver to drive an LED matrix and display the required patterns. And using ultrasonic distance sensor, we can measure the distance between the sensor as well as a particular object. So, as you can see here, there's a kind of dot pattern. So the left hand side shows one position of a dot and the right hand side shows another position of dot. So when you try to switch between these two patterns, it gives a kind of animation. So based on the distance measured, you could always um, switch between these patterns at different rates. I mean, the delay between two patterns or the two frames can be varied based on the distance to give a kind of animation which shows the dog as running or walking. So let us look into this in more detail. Now, if you see, MAX 7219 is interfaced using the SPI bus on Galileo. So let us just look into the code and understand. If you see, this is the main program. So we have two threads. So one thread is to read the values, the distance value from the ultrasonic sensor, and the second one is the B thread which writes a pattern to the LED matrix based on the distance measured. So let us just look into this. So to configure the SPI bus on the Galileo, so we need to configure 3 pins 42, 43 and 55. Let's just look in detail about the pin configurations. So when you look at 42, you make it low and the clock SPI1 underscore CS pin is activated. You make GPI 043 as 0. You make the SPI1 underscore MOSI pin of quad processor available, and you make GPI 55 pin 0. It activates the SPI underscore SCK or the clock pin available. So let us look into how we could use this SPI bus and write patterns to the LED matrix. First of all, we set the number of bits per word to be sent. So we use this variable. You can see it's 8 bits, and the speed that we set is 10 megahertz. And then we start writing different patterns to the LED matrix. So before writing different patterns to LED matrix, we have to configure the MAX 7219 driver to accept patterns. So if you see the data sheet of MAX 7219, yeah, there are different kinds of registers. You can see here the decode mode register, the intensity register, scan limit register. So before we can send any patterns to the LED matrix, we have to set these registers and configure it properly. The shutdown mode register always is by default in the shutdown mode, so we have to switch it to a normal mode, and then we have to set the decode mode register to no decode because we don't use any 7-segment LED display for decoding. Then we use the appropriate amount of intensity and set the intensity register to the favorable value, and then we set the scan limit register to scan all the 8 columns, and then we set the display test register to normal operation because at the start the LED matrix may be in the display test mode. In the display test mode, all the LEDs on the LED matrix are switched on or high. When we switch to normal operation, everything is made low. So after making the configuration, you send the particular buffer address and then value. You can see that here 0809, the decode mode register and its value. So you send 2 bytes to indicate the address of the address as well as the value, and configure the max 7219. And then based on the register, or based on the distance read from the ultrasonic sensor, we write the particular pattern to the LED matrix, and you can see the patterns out here. So the first column, second column, third column, up to 8 columns. So for each column we set a particular value, so when you write these values to 8 columns you get a particular pattern, and we can start switching between patterns to create a kind of animation. So this is the uh, LED matrix part, and now we're looking to how to read the distance from the ultrasonic sensor. And if you see out here, you have the uh, ultrasonic sensor interface to galileo board using the echo and trigger pins. So the trigger pin is interfaced to the 14 pin, and the echo pin is interfaced to the 15 pin. We give a pulse to the trigger pin for it to generate a ultrasonic wave which goes, hits the obstacles, comes back, and the echo pins reads the wave which is reflected back, and we effectively try to calculate the time difference between sending the pulse and receiving it back, and then we use the velocity of sound in air to try to determine the distance between the object and sensor. So we basically we use the pole function to pole on the echo pin, so to detect the rising and falling edges, and we calculate the time difference using the RDTSC, which you could see here. So once we pole on rising edge, once we start polling on rising edge, and after you receive a rising edge, you start recording the RDTSC value to get the start value where the edge has risen, and then you start polling for the falling edge. So when you poll on falling edge, it generates an interrupt, and then you know that the echo has ended. So you try to get the end RDTSC, and you try to get and then you get the difference between the start and the end RDTSC, and use the velocity of sound in air to get the distance between the obstacle and the sensor. Now we'll see how we are going to use this distance. Here we are going to use the distance to manipulate the time difference between switching each pattern, so that you get the walking or running pattern of the dog, as well as we use the distance or to measure whether to move the dog left or right. Here in my assignment I have configured it in such a way that you you come closer to the sensor. That means if your distance keeps decreasing, it moves left, and your distance keeps increasing, it goes right. So based on the distance value, you can manipulate the time difference between each frame as well as the direction in which the dog moves. So let us just look into how that is done when it is implemented on the galileo board. Now I am going to explain the execution of task 1. As you can see, the dog is running. When I move back, the dog runs slowly, and it turns right. And when I move forward, the dog runs fast and it moves left. Now we are going to talk about the second part of the assignment. Here as the assignment states, we move some of the operations from the user application to the device driver. So now we are going to write an SPI device driver to interface the LED matrix, and we are going to write a device driver for the ultrasonic sensor to measure the distance, because this speeds up a lot of operations, because it reduces the number of system calls used from the user space and all that. So basically you can always speed up the operations and get more accurate values from the distance sensor. Now the assignment states we have to send a pattern of the particular format 0, 100, 3, 200, 00, pattern displayed here. So this indicates that the pattern 0 has to be displayed for 100 milliseconds, and then pattern 3 has to be displayed for 200 milliseconds, and then 00 indicates that it's the end of the pattern sequence, and we have to loop back to the starting position and start displaying the patterns from there. Now let us just look into the various drivers and the user application that we developed to use those drivers to work with the LED matrix as well as the ultrasonic sensor. So if we look into the main task, here we use the /dev/pulse, which is the ultrasonic sensor driver, as well as dev/SPI_LED, which is the LED SPI driver that we developed to use the SPI LED matrix. So to start off with, we have a buffer which has 10 patterns. So for our assignment, what I've used is a walking or a running dog, and it doesn't even have a left or right. It's a very simple animation. So the first two patterns would be the walk and the run kinds of patterns, the two patterns that are given here. So the first pattern will be this, the second pattern will be this, and rest of the 8 patterns are basically garbage. So, and then we send these set of 10 patterns into the kernel space so that the driver can buffer them and use them based on the patterns that we write to the LED matrix. So we send the 10 patterns using an IOCDL command. So now we're looking to the SPI LED, and you see that we have set the 42, 43, 55 to the particular respective low values so that the SPI1 bus gets activated. And now we are going to see the IOCDL command that we use to transfer the buffer of 10 patterns. So here you see the test 10 pattern. We copy from user space the array of 10 patterns, which is 160 bytes, because each pattern has 16 bytes, and 10 patterns occupying 16 bytes each sums up to 160 bytes. So we copy the 10 patterns from user space to kernel space, and we buffer them in the pattern called LED buffer. And this is just a print test case to check whether we have received our buffer or not. And then we set up our SPI pins, and then we start a kernel thread because we don't want our SPI LED to be blocking. So we write a non-blocking thread, kernel thread, so that it displays continuously. So the basic function of the kernel thread is to accept the pattern that we send from user space, for example of this kind, and then display the appropriate patterns and make a delay for appropriate amounts of time based on the pattern that we send. As you can see here, it accepts the buffer, and then it writes the particular pattern to the LED display, and then it makes a sleep for the amount of time that we have sent to the packet, and then it displays the second pattern until we get a 0, 0 in the pattern, which indicates that we have the end of patterns and we have to loop back. So this is a continuous process, and using this we keep continuously displaying patterns based on the numbers that are being sent in from the user space. Now we'll look into how we are going to handle the distance that we get from the ultrasonic sensor to handle the animation in the SPI. So if you see, we basically set our GPIO pins, 30 and 31 make low so that we get access to the quad GPIO pins, and then we use 14 as the trigger, 15 as the echo pins, and then we register an interrupt handler on the 15th pin so that whenever we get a rising or falling edge we generate an interrupt, and then we record the RDTSC values, and which is more efficient actually in this way. So let's look at how the interrupt handler works. So basically when the interrupt handler is invoked, we see that we have a rising edge, and then we get this start value of RDTSC, and then we change our trigger typing to falling so that the interrupt handler generates an interrupt when a falling edge has occurred. And then when a falling edge has occurred, we just take the end value of RDTSC, find the absolute difference, and using this absolute difference we try to calculate the distance using the velocity of sound, and then we try to make our animation. Here in our dog animation, I've taken the distance to vary the time or the delay between two patterns. So when the distance is near, your dog seems running, and when the distance is far, your dog seems walking. So this is a very simple kind of animation, and using this assignment we have got to know about SPI, LED matrix display, interfacing the ultrasound sensor, and we got to know more about the interrupt handlers and kernel thread. So thank you for watching this video, and next will come up the live deployment of the task 2 on Galileo board. Thank you so much. Have a good day. Now I am going to explain the execution of task 2. As you can see, the dog is running right now. When I move closer to it, it starts running faster, and when I move it further back, it walks slowly. You can see the animation. The transition with the dog from running to walking, walking to running. Thank you.